Welcome to NASA's Jet Propulsion Laboratory in Southern California. NASA's Perseverance rover is currently investigating a geologically rich area on Mars and has successfully acquired several rock samples. I'm Raquel Villanueva with the JPL Digital News and Media Office. I'll be your host today as we discuss the samples the rover has collected on the Red Planet. Our speakers today include Laurie Glaze, Director of NASA's Planetary Science Division, NASA headquarters. And here on stage, we have Ken Farley, Perseverance Project Scientist, Caltech in Pasadena, Sunanda Sharma, SHERLOC Instrument Scientist, JPL, Rick Welch, Perseverance Deputy Project Manager, JPL, and joining us virtually is David Shuster, Perseverance Return Sample Scientist, University of California, Berkeley. Now, we'll be taking questions after hearing from our speakers. If you're a member of the media on the phone line, press *1 to get put in the queue. And if you're watching on social media, use the hashtag AskNASA to ask a question. And we have members of the media in the audience today. Welcome. If you have a question you'd like to ask, raise your hand and we will bring a mic to you. Now, before we get started, we'd like to set the stage with some opening remarks. So please welcome JPL Director Laurie Leshin.
Well, welcome everyone and good morning. So just over 18 months ago, Perseverance landed on Mars in the middle of a global pandemic and caused us all to look to the sky and remember and reimagine what's possible. Now, over 550 sols, Martian days later, this amazing rover has collected a really tantalizing suite of rocks with extraordinary science potential and really whetting our appetite for what's next. And that's really what we're here to celebrate and talk about today. That does not just happen. It happens through the collaboration of folks across disciplines, across organizations, across continents, and we're celebrating that as well. They have brought Mars into sharper focus than ever before, and I want to just give huge kudos to the team here at NASA, at JPL, across academia, across industry, across our international partners. And while Percy has ignited imaginations everywhere, I will say it's especially ignited mine. As a 10-year-old girl, I was riveted by the first images of Mars sent back by the Viking landers. I loved those red rocks and I wanted to reach out and touch them. And that has really animated my whole career. And you'll see that we are doing better and better at querying those rocks and finding the most interesting ones. I'm especially thrilled at where we are today with Perseverance. And building on that legacy of Viking, 25 years ago, we landed Mars Pathfinder with its Sojourner rover. And since then, we've been getting more and more sophisticated in exploring the surface of Mars with better and better instrumentation, better and better roving capabilities. And we have been building towards what we're going to talk about today, collecting the most exciting suite of samples that we can manage. That has been building up over time for us to get to this point. We've been working towards that so that we can bring these rocks back to Earth, where we can query them in the most sophisticated laboratories that we have so that we can get at answering some of the biggest questions that we as scientists can ask. Really, to undertake the challenge and the expense of a Mars sample return mission, we need a great suite of rocks to bring back. And that's what you're going to hear about in today's briefing. I hope you all will agree with me that we are off to a great start in that goal. So to say that I'm thrilled as someone who's been working towards Mars sample return for, frankly, a couple of decades, to say that I'm thrilled with where we stand today, it would be a huge understatement. So again, huge kudos to the team. So onward Perseverance, onward Mars sample return, and thanks to all of you for joining us today to hear the exciting news from Mars. And now I'd love to hand off for a few words from the head of science at NASA, one of the greatest supporters of this mission and others, Thomas Zurbuchen.
Hey, I'm Thomas Zurbuchen, the head of science at NASA, and I'm so excited, together with the Perseverance team, to really celebrate this huge achievement. We've been on the surface of Mars for over a year now, have collected 12 samples, and have learned a lot about this amazing region called Jezero Crater. I remember the first time I saw this, it was one of the target landing sites, and frankly, the most hazardous ones of all the sites. One that really required terrain relative navigation on the way in during the landing to absolutely work. Of course, all of that is history. We have landed successfully. That technology did work. And frankly, we landed a little bit off to the side because of that technology that saved us from being in a kind of doom field, which of course we don't want to be. That technology also got us to sit there and actually explore a region that has already been the subject of a number of publications. And with the samples that we're taking now in this more sedimentary area, we of course are right at the heart of what we wanted to do to start with. Look at areas where on Earth we would look at to actually see whether there's fossil life. I remember as a child playing in a place like this that used to be a coastal region elsewhere, now in the central part of Europe. So really excited for the results, and of course in my mind I'm also thinking of the international team that is going to bring those samples back to Earth with 2 missions in the late 20s. So in the early 30s, these amazing samples can be analyzed with the best labs available to humanity right here on Earth. Congratulations, Perseverance team.
Thank you, Laurie and Thomas. We'll now hand it over to Ken.
Thanks very much, Raquel and Laurie and Thomas. It's a pleasure to be here today and to have the opportunity to tell you about what we've been doing over about the last 5 months when we've been exploring a region that we call the Delta Front. If I can have that first image, I want to remind everybody that Perseverance is exploring Jezero Crater, and this crater held a lake about 3.5 billion years ago, a very large lake, about 40 kilometers across. And the evidence for that is very clear in this first image. On the west side of the image is the crater rim. This is about 1 kilometer high. And you can see that that crater rim is breached by a canyon. That canyon transported water into the lake, and it also transported sediment. And when that sediment was brought into the lake, hit the slack water of the lake, the sediment deposited and formed the delta, the feature that's labeled on this image. That's where we have been working recently. Jezero was selected for this mission because it meets several key mission goals. It allows us to explore an ancient habitable environment. It allows us to seek evidence of possible Martian life in rocks deposited at that time, about 3.5 billion years ago. And I want to emphasize, this mission is not looking for extant life, things that are alive today. Instead, we're looking into the very distant past when Mars's climate was very different than it is today, much more conducive to life. So we are looking for ancient life. And as you already heard from the previous speakers, we are preparing a diverse suite of samples for potential return to Earth by future missions. And I want to emphasize the idea of diversity. The objective of diversity is to allow these samples, when they come back, to be studied for a huge range of topics, not just astrobiology. There are a huge number of questions that can only be answered by samples that are brought back to Earth and investigated in terrestrial laboratories. So I'm happy to say that we have made excellent progress towards achieving the goals that I just laid out. We've also managed to piece together quite a detailed history of Jezero Crater, a history that is surprising. It's not exactly what we expected. The image that you see now also shows the route of the Perseverance rover in its 18 months on Mars, the white line. The region with the red star is where Perseverance is today. In the first year of the mission, we undertook what we called the crater floor campaign. That's on the southeast part of this traverse. This was exploring the crater floor, the rocks that are below the delta. And what we found is not what we expected to find. Many of us expected to find out there in the middle of this crater that once held a lake, we expected to find sedimentary rocks deposited in that lake. And instead, what we found is igneous rocks, rocks that were crystallized from a melt. So that suggests a history that is more complicated than we expected. This crater not only held a lake at one point, but prior to that, likely prior to it, it also had active volcanism and possibly even a lava lake filling that crater. So there's some complexity there that we hadn't actually expected. And we acquired some excellent samples of those igneous rocks. And this is an example of why diversity is important. Those igneous rocks will tell us a lot about the early history of a rocky planet, Mars. And in addition, one of the key things that an igneous rock return to Earth will allow us to do is for the first time put a quantitative age on the surface of Mars. This is something that we just infer indirectly at present. So it'll be very important to get quantitative estimates of age on returned igneous rocks. After we finished the crater floor campaign, we drove very quickly in that arc around to where the rover is today at the delta front. If I could have the next slide, please. So the delta front is a scarp cliff about 40 meters high. You can see that we have driven back and forth studying this place. It's a really interesting place. And the reason it's interesting is that the delta is a place where the sedimentary layers deposited in that lake are exposed in cross-section. So rather than just driving around on top of those sedimentary layers, we can actually drive up and see them one by one. If I could have the next image. This is from the area that you're going to hear a lot about. It's called Hogwalla Flat, and you can see putting down a subset of them on the surface of Mars as a target for the future missions to pick up and bring back to Earth. So good progress overall, and with that, I'll turn it over to David Shuster.
All right, thank you, Ken, and good morning, everyone. Can everyone hear me okay? Okay. Yeah, so as Ken mentioned, we've spent something in the order of 5 months exploring this delta front region. And you saw the rover traverse in that first map that he showed. This image that you're looking at I like very much because the team worked very hard to find 2 different types of samples to collect from the delta front, and we ended up finding them only about 20 meters apart. These 2 rocks, named Skinner Ridge on the right and Wildcat Ridge on the left, are very different. They each have high science value for quite different purposes that I'm going to explain. Skinner Ridge, as Ken mentioned, is a sandstone. It's a fine to medium-grained sandstone. It contains, importantly, a quite diverse mixture of lithologies, meaning that it has a whole bunch of rocky material that was potentially transported into Jezero Crater from hundreds of kilometers outside Jezero. That's important because this is giving us material from a very far distance that the rover will not visit in this mission. Wildcat Ridge on the left, on the other hand, is a very different type of sedimentary rock. It is a fine-grained sulfate-bearing mudstone that also contains clays. And interestingly, this appears to have formed in salty water, possibly during the lake evaporation stage. So at some point, the lake filled up with water, and as that evaporated, it appears that this rock on the left formed. This is really important that this has sulfate in it and also clays, because that means that this rock has high potential for biosignature preservation, meaning that if there were biosignatures in this vicinity when that rock formed, this is precisely the type of material that will preserve that for us to study when they come back to Earth. So what we have here is both of these rocks are composed of sediments that were transported by liquid water. They were both deposited into a lake, and then they subsequently experienced aqueous alterations also involving water, and cementation after deposition. Thus, these rocks formed in and record conditions of a habitable environment. And the next slide, please. In this image, you can see the layering that Ken mentioned up on Rocky Top, and I'm just showing you this because you can see the rover arm, and you can see Skinner Ridge in the lower part of this image. And if you look, you'll notice that there's an abrasion patch. There's a very light-colored circular position in that rock that I'm going to zoom in now. So if we can have the next slide. And what you're seeing here is a close-up Watson image of this abrasion patch. And every time I look at this sort of image, let's remark on how absolutely wonderful this is. We were looking at a very, very small region of space. Notice the 5 millimeter scale bar. This is on Mars, right? And we're looking, and Sunanda is going to show us even a higher resolution image. We're looking in very, very fine detail. And what I'd like you to notice in this rock is that there are color variations that we can see. And we can also see that there are grains that appear to have been rounded. These indicate that this material, this sediment, these bits of Mars in the rock form have been transported down a river and deposited into Jezero Lake. Can I have the next slide, please? And this image here is just showing that the two cores that we collected from that rock are absolutely fantastic. It does not get any better than this. What you're looking at is the bottom of the core after we drilled it out of the rock, and both of these cores are full. They're as nice of a core as we have collected on this mission. And importantly, these materials will enable all sorts of science to happen, as Ken mentioned, upon return to Earth in laboratories on Earth. And importantly, we can determine when each one of these little bits of rocky material crystallized in this rock. In addition to that, we can also determine when the cementation, when this rock was cemented together in principle. We can learn a lot about the chemistry of the fluids that transported this rock, things like the temperature of that cementation. So we can learn a lot about when this material was deposited. Can I have the next slide, please? So this is now showing an image of the Wildcat Ridge, the other sampling location. And what you see in this image are the abrasion, that circle on the right, that we'll hear more about from Sunanda in a minute, and those two core locations on the left. So once again, we had an absolutely successful coring at this rock. Can I have the next slide, please? And these are the two cores from this rock. Again, the cores are both full. These are essentially slam dunk in terms of coring these two very important rocks at the front of the delta. Can I have the next slide, please? And now when you look at the close-up Watson image on the right of the Wildcat Ridge, I hope that you can all see that these are two very different looking rocks. Specifically, you can see that the one on the right is much lighter in color. It's relatively uniform, and it is fine-grained. As I mentioned, it is also rich in sulfates. And all of this is very important because these are the ingredients, these are the qualities of rock that we're looking for that have high potential for biosignature preservation. So to summarize, both of these samples that we've collected from these two rocks record a paleoenvironment and environmental conditions of a formerly habitable environment. Both of these have very high scientific value for the next generation of scientists when these return to Earth to be studied in the laboratories that you've heard about. I think it's safe to say that these are two of the most important samples that we will collect on this mission, and we're all very excited about what we've found. And I'll pass it over to Sunanda now, who will tell us more about the Wildcat Ridge observations on the right.
Thanks, David, and hi, everybody. It's great to be here. So I'll talk a little bit more about the science at Wildcat Ridge. So the observation of organic matter at Wildcat Ridge was made by one of the instruments that's on the rover arm that you can see highlighted in the image, which is called SHERLOC. SHERLOC gives multiple types of information. We have color images and black and white images, and also spectra. Spectra are basically signals that result from light interaction with a rock surface. The light that we use is a special type of laser that you can think of as a fancy black light, and it helps us see things in the rock that would otherwise be invisible to us. The images that we take with SHERLOC's two cameras provide visual context for where the laser hits in a map. So when SHERLOC studies a rock surface, it shoots its laser in a pattern across an area that's about the size of a pencil eraser. Can I have the next image? Yeah, so when the laser lights up different components in the rock, that includes chemicals, minerals, and organic matter. And organics, as you heard from Ken, are commonly called the building blocks of life. All life, as we know it, is made up of organics. But importantly, organic matter can also be made up by processes that are chemical and they're not related to life. So for instance, through water-rock interactions. And it's also found in interstellar dust. By putting together the image and the spectral information it collects, SHERLOC can map where organics and minerals are in a rock, which tells us more about how the organic matter was formed, transported, preserved, or concentrated. Organics tend to form clumps. We've seen this on Earth and in Martian meteorites, and unless you can map, you miss some of that key information. This is the first instrument of its kind that's operating on Mars, and it gives us very important information from rocks as they are found in place to support the selection of samples for the return to Earth. So can I have the next slide? Thank you. SHERLOC studied the abrasion patch on Wildcat Ridge on two different sols, or Martian days, Sol 505 and 513. We performed about 8 scans on the patch overall. The abrasion patch, as a reminder, is on the same rock of where we sample, but it's not the exact same spot. It is a good proxy, however, for what we are picking up in the rock core, and it gives sort of a preview of what might be observed when we bring those samples back to Earth. In Wildcat Ridge, we detected signals that we think are from a class of organic matter called aromatics, which are stable molecules that are made up of carbon and hydrogen and sometimes other elements with ring structures. These signals were present at nearly every single point in every scan. They are also some of the brightest that we've seen thus far on the mission, and they're about 7 times brighter than what we saw at Thornton Gap, which is an abrasion patch on Skinner Ridge. And so the organic signals are also most strongly correlated to a mineral called sulfate that we saw in the rock. This correlation suggests that when the lake was evaporating, both sulfates and organics were deposited, preserved, and concentrated in this area. So while the detection of this class of organics alone does not mean that life was definitively there, this set of observations does start to look like some things that we've seen here on Earth. So on Earth, sulfate deposits are known to preserve organics and can harbor signs of life, which are called biosignatures. This makes these samples and this set of observations some of the most intriguing that we've done so far in the mission, and it fulfills some of the excitement that the team had when we were approaching the Delta Front. So when we put this finding into context of all the other observations we've done with SHERLOC so far, which is 13 other targets we've observed through the crater floor and in the delta, it's clear that we are uncovering a bigger story that's happening in Jezero Crater. So we found signals that we think are possibly from organic matter on every target that we've observed with SHERLOC to date. And this isn't really unexpected. It aligns with what we've learned from studies on Earth and Martian meteorites and from Mars research from our sibling rover Curiosity. However, it does say that organics seem to persist in the very harsh Martian surface environment, which is very exciting for us. And as we've made our way from the landing site to the Delta Front, SHERLOC has seen this particular signal associated with sulfates in a couple of other places. So at first we saw this at just a few points in a couple of scans in a couple of targets in the crater floor. And as we're moving into the delta, these sort of hints are becoming stronger and stronger, and to the point that now, as I've said on this rock, we're seeing it in every single point on every scan. And so, to put it simply, if this is a treasure hunt for potential signs of life on another planet, organic matter is a clue, and we're getting stronger and stronger clues as we're moving through our delta campaign. I personally find these results so moving because it feels like we're in the right place with the right tools at a very pivotal moment. Mars 2020 is giving us a better understanding than we've ever had of the Martian surface to select samples for return. And then Mars sample return stands maybe the best chance ever of answering a very profound question: are we alone in the universe? We are building on a legacy of interdisciplinary and multi-scale research that's been taking a progressively closer look at Mars. Our understanding of the planet bridges across scales, from the orbit all the way down to this view that you're seeing from SHERLOC, which is one of the closest we've ever had to a rock on the Martian surface. And it really highlights to me that perspective and context bring meaning to our findings. The strength of each instrument on this rover really came into play on this rock. So on Wildcat Ridge, we now have chemical, mineralogical, elemental, textural, color, and stratigraphic data to help provide some context to anchor what our findings are. And this gives the most detailed information possible for across scales and observational axes for Mars sample return. And it just feels surreal to be part of the science team that's doing these observations. I get to come to work and look at data from another planet every single day, real data that's coming down from another rock on another planet. So for years, I've been hearing about this delta and all of its promise, and it's deeply encouraging that now that we're here, the data is actually matching our expectations. So with that, I'll pass it over to Rick.
Thanks, Sunanda. I'm going to talk a little bit about what Perseverance is doing right now and what we're going to be doing in the future. Let me just say that it's very early morning on Mars right now, Sol 559. That's the 559th day of Mars, and Perseverance is probably still fast asleep, awaiting her next command load of things that she'll be doing in the day. Very productive mission so far. We've driven 13 kilometers, over 13 kilometers. That's over 8 miles. And as mentioned before, we have 15 sealed tubes on the rover. So let me just remind folks what a tube actually looks like. And inside these titanium tubes is we can store about a pinky-sized rock right inside there, right? And so we have 15 sealed tubes on board the rotor. We brought 43 tubes total. We also have a sealed tube, which is no rock inside, just an atmospheric sample. And we also have 2 witness tubes that are a measure of contamination that we can do along the mission as well. Let me also mention that Ingenuity is also doing very well. That technology demonstration for a helicopter on Mars, only designed for 1 month, and has survived 18 months into the mission, which is very exciting for us. It is winter, though, and Ingenuity was never designed to live through winter. It has been an energy challenge, and we're carefully monitoring that. It does look like the energy is going up for Ingenuity, and we were just last week able to do a short hop of 100 meters, showing Ingenuity is fully functional. So we're very happy with that, and hope Ingenuity continues along with us in our journey. So let me look at this first graphic here. Ken already showed this with the current rover location and the tracks of the rover exploring the delta front, going back and forth. We've just arrived back at Enchanted Lake here, and our plan for the next 2 months is to get several more samples, a pair of rock samples, as well as a pair of regolith samples, and another witness tube assembly. So this will bring our total of tubes on board the rover of 20 sealed tubes out of the 43. And I mentioned pairs of samples, so let me say a little bit more about that. We've actually had a pairing strategy from the very beginning of the mission. And so every rock we've gone to, we've actually gotten 2 samples from those rocks. And that allows us to have one for an initial cache depot on the surface of Mars that we can put down and then maintain that second sample on board the rover. So in the middle of this graph, this is actually where the possible first drop location for our samples to the first depot that we may form on the surface of Mars. So we go to the next graphic. And so about 2 weeks ago, we took this image looking back at where that potential depot location would actually be. You can see the rover tracks crisscrossing across this area. And one of the notable features about this area is how smooth and flat it is. Right, and so over the past 6 months, we've been very closely working with the Mars sample return teams, looking at this area because, of course, they have to have the job of actually successfully landing here and retrieving the samples. And this really is an ideal location. Very flat, very few rocks, a great place to land, and a great place to actually be able to retrieve sample tubes. So we're looking at the potential of putting down 10 to 11 sample tubes here on the surface. And then that would take about 2 months to probably put those samples down and actually carefully document where they are so the future mission can actually find them. So let me talk now a little bit more about the future. So if we could have the next graphic. So what would happen after we put down that depot would be further exploration. Right, we still have a set of samples on board. Where we want to go is up on top of the delta. So this dark black line shows potential traverse paths we're actually looking at to explore the top of the delta, gather more samples, and get all the way over to where the edge of the lake was here in Jezero Crater, shown there near the crater rim on the left of the image. That's probably going to take at least the next year of operations to do that exploration. But we do even want to go farther than that. Let me just remind folks that Curiosity just celebrated the 10th anniversary on Mars. Right, and Perseverance is, designed exactly like Curiosity. We expect a very long mission for Perseverance as well. And so our long-term plan is to climb up the crater rim, to go beyond Jezero, and explore and sample the area beyond that, and to have the potential to actually rendezvous with the Mars sample return missions in the future and actually deliver all the samples we've acquired at that time. So a very exciting prospect for the future. And with that, let me turn it over to Laurie.
Great. Thank you so much, Rick. Appreciate it. So just from everything we've heard here today and just the complete body of work that's been completed by this incredible Perseverance team to date tells me that we not only went to the right place, but we sent the right spacecraft with the right science instruments to explore this amazing ancient environment on Mars. Ever since Perseverance's very first core was collected, we've said that the Mars sample return campaign is underway and progress continues to be made, as you're hearing. So the Mars sample return campaign, it could really revolutionize humanity's understanding of Mars, by returning these scientifically selected samples for study using the most sophisticated instruments from around the world. So let's talk just a little bit about what's going on with that next phase of the Mars sample return campaign. We've recently made some changes to the campaign design, and if I can get the first image there, you can see our Mars sample return family portrait. Mars sample return, of course, this is a strategic partnership with the European Space Agency, and it'll be the first mission to return samples from another planet, and also the first to launch from the surface of another planet. The samples to be returned, those that are currently being collected by Perseverance now during its exploration of Jezero Crater and its ancient river delta, those samples are thought to be the best opportunity to reveal the early evolution of Mars, including the potential for life, as you've already been hearing here today. In this image, you can see Perseverance, who's not only collecting samples, but can be utilized to deliver the samples back to the sample return lander. In fact, based on a new assessment of the reliability and life expectancy for Perseverance, we now have increased confidence that the rover will be able to deliver those samples to the lander in the 2030 timeframe. That lander, the lander that we're going to deliver the samples to, is going to carry a payload that includes 2 sample retrieval helicopters. Those helicopters are going to build on this incredible experience we have with Ingenuity. And those little helicopters will be able to retrieve the samples that are left on the surface at the caching depot that Rick was just talking about. The lander will also carry the Mars Ascent Vehicle, which will place those samples into orbit around Mars for capture by the European Space Agency's Earth Return Orbiter. So we're making tremendous progress in maturing our plans for Mars sample return. And if I could have the first video clip, please. This video is showing some testing that's going on in JPL's Mars Yard with the Perseverance test bed known as Optimism. The goal of this set of tests was to practice dropping the sample tubes from the adaptive caching assembly to the ground on variously tilted terrain. This is the same procedure that'll be used when we drop the tubes on Mars. And this allows us to then design and test the systems, those systems, so that we can successfully pick up the samples from the surface. And if I could have the next video clip, please. This video is showing some ongoing testing of the updated sample return lander landing gear. This test, using a 3/8 scale model of the sample return lander, was specifically aimed at the legs supporting the lander structure with impact speeds of about 1.5 to 2.5 meters per second. These tests are still ongoing. The latest test just took place a week ago. And the approach with this testing is to carefully construct the physical tests in the physical world and then construct the same exact tests in a computer model. And that way, we can make sure that the computer simulation matches what happens in the real world tests. And then that lets us know that the computer model is correct, and we can use that computer model to simulate thousands of landings on different slopes, rocks, ground types, orientations, to understand and predict how the lander would behave on Mars. So looking to the future on MSR, there's a few things coming up in the near future. Just next week, we'll be testing the thermal protection material conductivity out at the Ames Research Center. Also in September, on the 28th and 30th, we'll be holding a science workshop that's open to the public to discuss ideas about the deployment of the MSR cache depot. So there'll be a lot of discussion about that caching activity. And then following that workshop on October 19th, there'll be a go, no-go decisional meeting that'll confirm that we are ready for dropping those samples at the depot. In November, a little bit further on the horizon, the European Space Agency's member state ministerial meeting is going to happen. At that meeting, we expect our partners, the European Space Agency, that they will finalize their architecture decisions for Mars sample return. So I mentioned earlier, we've been saying that the Mars sample return campaign began with Perseverance's exploration and the first sampling at Jezero. And what an amazing story those samples are telling us. Not only the Wildcat Ridge samples, but the entirety of Perseverance's samples are intriguing, which means they're perfect for Mars sample return. Perseverance collected both water-deposited rocks and igneous rocks, leading to a highly diverse sample suite. And that diversity is central to the objective of Mars sample return, because the more diverse the sample suite, the more diverse the science investigations the samples are going to support. So with that, I want to thank the entire Perseverance team for all of their hard work. And back to you, Raquel.
Great. Thank you, Laurie. Now, it is now time for questions. if you're a member of the media on the phone lines and have a question, press *1 to get put in the queue. And if you're on social media, use the hashtag #AskNASA. But first, I'll take a look in the room and see if anyone has any questions. If you do, please raise your hand, and we will bring a mic over to you. Looks like I'll give some people a chance to get ready. Let's take it to the phone lines. We have Maria Koren with The Atlantic.
Hi, Marina Koren with The Atlantic. For Ken, a question about finding more igneous rock than you expected. You said that this means that before there was a lake in Jezero Crater, there was magma and lava. But I'm wondering if this discovery has made you reassess your current understanding of a lake here. For example, does this mean that the ancient lake was more short-lived than we might have expected? And a quick one for David, how does this igneous rock affect the story of how the lake even got there? You said the lake filled up, but how? Maybe this is a very basic question, but how did the lake even get there based on what you're seeing? Thank you.
So we have an indication that there is a significant amount of material that was deposited in this crater after it formed. And it is undoubtedly, now we know, it is a mixture of different kinds of things, including the igneous rocks that I described, as well as the sedimentary rocks. And the reality is, all we can really know is what's exposed at the surface. So whether there are lake deposits that lie below the igneous rocks, we don't know. The question of how long the lake was present, this is an important question, and it is very difficult to determine that with the rover. This is the kind of thing that we are hoping to do with the return samples. So it doesn't make us doubt the existence of the lake, but I'll let David address that question.
Yeah, I echo everything that Ken said. You know, one of the key variables that we really don't have much knowledge on is the time dimension, right? And so I think one of the important implications of the igneous rocks, first of all, let's be clear, the igneous rocks at the crater floor, at least some of which we collected, we think are clearly beneath the delta. So that means they were emplaced before the delta was emplaced, which at face value indicates that those were in place before the lake was present, or at least this iteration of the lake that we're observing. And so the key variable there that we really don't know is how much time we're looking at. For all we know, there could be hundreds of millions of years or more between when those igneous rocks were emplaced and then when the delta was emplaced on top of it. So I think to answer your question, if I understood it correctly, is it really doesn't have much bearing so much on how the lake formed, but it will have very important implications that, as Ken said, we will be able to quantify when these samples come back to Earth about when the lake was there, and then ultimately that will help inform our understanding of how long the lake was there, how many times the lake filled up, for example. Hopefully that answers your question.
Right, thank you. We'll now move on to the second caller, which is Bill Harwood with CBS News.
Hey, can you guys hear me? I'm sorry.
We can hear you, Bill.
Oh, hey, thanks. I just wanted to follow up on that very same question. I'm a little fuzzy about the richness in the organic material you're finding at the base of the delta, and then the transition from there out into the more igneous deposits toward the center of the lake. I'm still not understanding, I guess, the possible history here of lake versus, magma versus, whatever hit Mars in the first place to excavate the crater. I'm still not quite getting that. What you think the history might be? Thanks.
Okay, I'll give a quick summary, and if Sunanda wants to jump in, she can. The basic idea is this crater formed. It probably formed about 3.8 billion years ago. It made a big hole, and that hole is filled with material, as I mentioned, but we don't know the origin of that material. But one of the key things that is special about Mars is how long surface features persist. Without plate tectonics and the kinds of reworking that we see on Earth, features last a long time. So as David suggested, there may have been multiple iterations of lake the lake might have filled and dried up, and then there might have been magmatism filling it up with lava, and then more lake. So all we can really say is that there is evidence that there are igneous rocks that are older than the final iteration of the lake that we see that made the delta. What happened before that, we don't know, but it's basically a time history, the bottom of which we see is the igneous rocks, and then the upper part of which is the delta that is the last iteration of the lake.
Yeah, I'll add in there a little bit more about the signals that we think are from organic matter. So I guess there's a couple of different metrics that we use to determine in that map that you saw, in a SHERLOC map, how much we're seeing and what is the diversity of signals. And so in both those different metrics, like how many times we're seeing a signal, the intensity of the signal actually, and the diversity of the different types of signals that we think could come from organic matter, we're seeing what we saw on the crater floor and what we're seeing in the delta as two different things. The exciting thing that I was mentioning is that we saw almost hints of now what we're seeing so loudly, so clearly in the delta as we are moving through the crater floor. So there's a relationship there, but these are two different distinct things.
Thanks. Hope that answered your question, Bill. We are now going to switch it over to social media, and I'll hand it over to the JPL social media lead for questions.
Yes, thanks everyone. We have so many great questions coming in. The first one is a question on the timing for the return of these samples. We actually have a few of these questions. Adam on Twitter asks, super exciting. A return mission would be very complicated and probably decades away, unfortunately. And to follow up on that, Melissa from Facebook asks, how long will the return trip take with the samples so we can study them?
I'll take that one. Those are some great questions. And what's really exciting is that we have the technologies now to bring these samples back. I think this is just amazing. I think you heard Laurie Leshin at the beginning perhaps say, that we are now really in the position that these samples are so compelling that we want to get them back. The Mars sample return campaign that we're working on, as you say, is incredibly complex, but we expect to have 2 launches from Earth later this decade. The Earth Return Orbiter that'll carry the samples back to Earth is expected to launch in 2027 in our current design. And the Sample Return Lander will actually launch a little bit later, a few months later, in the spring of 2028. It'll arrive on the surface of Mars and spend a relatively short amount of time, hopefully, with Perseverance bringing samples, delivering them to the rover, or having the helicopter pick them up and bring them back to the lander. And then we will launch those samples into orbit around Mars. This will all happen around 2030. And then it begins the trip back to Earth. And we expect those samples to be back on Earth in 2033.
Thank you so much. And a question for Ken. Mike on Twitter asks, can Perseverance detect signs of life without samples being brought back to Earth?
Yeah, that's a great question. And it really goes to this point that I was making about potential biosignatures. There's another kind of term that we would use, which is definitive biosignature. So a definitive biosignation is something that is undoubtedly due to life. And so the way I understand that question to be, what is the likelihood that the instruments aboard the rover will definitively detect evidence of life? And the reality is the burden of proof for establishing life on another planet is very, very high. And it seems unlikely to most of us that the evidence will be so compelling that we will be able to do that. And I just want to make the point, the rover can only make the kinds of observations that we thought of building into the rover years ago. That's very different than terrestrial laboratories where you can say, well, if we just make this kind of observation, some new thing that we hadn't thought of, that'll answer the question. Rover can't do that because the rover only has what it has. So this is one of the reasons why bringing samples back to Earth is so important. So in answer to that question, I think it's not very likely that we will make a definitive detection of life. About the best we are likely to be able to do is this potential detection.
Thank you for the social questions. If you want to ask a question online, use the hashtag AskNASA. We'll now take it back to the callers. Up next, we have Ken Chang with the New York Times.
Hi, thank you. A few years ago, there was a live segment about Curiosity finding organic matter in Jezero Crater, and that turned out to be ambiguous, and then the organic compounds weren't that complex. could you compare those findings with what you have now? How much is there of a more complex molecule?
Yeah, I can take that. So it's an interesting point and a really good question. So the technique that Curiosity uses to detect organic matter is different than what I mentioned with SHERLOC. So there are two different types of techniques, and actually SHERLOC has two in itself. So it's not exactly a head-to-head apples-to-apples comparison. And so that's, in order to really get down to what they're seeing versus what we're seeing and the concentrations, we need to go through the data a little bit more and then also bring the samples back would be the only way to be really, really definitive about it. But what I can say is the technique that we're using is really important because we're not breaking up the rock at all. We're observing it basically, the only change that we make is abrading the surface down. And actually we even do observations on rocks where we don't do that. So we think that what we're seeing in the rock, especially when we see organic signals associated with a mineral, we think that really was in the rock and it was formed at the same place or concentrated within a mineral. So we have some confidence that the organic matter we're seeing is actually in the rock, and I feel quite confident saying that.
Okay, thanks for the question. Up next on the phone lines, we have Mike Wall with Space.com.
Thank you all. Just a quick question to put these organics into a little bit more context. Can you compare the sort of concentration of them to what we might find on Earth in a river delta here? Or is that sort of comparison even worth doing because it's so kind of apples to oranges? Thank you.
Yeah, I think that's a good question. So Earth is funny and great because it's just teeming with life. If you went to a river delta, there's probably so much there. And there's so much there that's currently living, right? There's probably older signs of life, but then there's just tons of stuff that's currently living there as well. So it's really hard to find an example where there's not that much life on Earth in a river delta that would be active. So it's a really different situation. And as Ken said, we're looking for ancient signs of life. So we think that all of this was happening billions of years ago. So it is a really, really different type of comparison, but mainly because of the time difference that we're looking at. So it's a more challenging case on Mars, and we're still learning from things on Earth. So for instance, in Earth labs, we look at things like Martian meteorites, and that gives us a good understanding of what sorts of minerals we would observe and how organic matter is placed within those minerals. And of course, we do have analog sites on Earth that we think are somewhat representative of Mars that help inform our understanding of what we hope to see on Mars.
Point to that? Hopefully you can hear me. The way that I think about this is these samples that we've collected, as we presented here today, have ingredients for life in terms of the environmental setting. This material was transported by water, was deposited into a lake. We have fine particles that were settling out of that lake. We have phases that were formed during evaporation of the lake. All of these things, as we've discussed, have high potential for biosignature preservation. If these conditions existed, I think, pretty much anywhere on Earth at any point in time over the last, let's call it 3.5 billion years, I think it's safe to say, or at least assume, that biology would have done its thing and left its mark in these rocks for us to observe. And so that's really why we're so excited to be able to address these questions upon returning these samples to laboratories here on Earth. We have all of the right ingredients here.
Great, we could hear you, David. And the next caller is John Amos from the BBC.
Hi there, thanks for doing this. Can I just talk about your future drive? There was a lot of discussion before we landed about the bathtub ring, which from memory was on the northern side of the delta. We don't appear to be going anywhere near that. Why is that?
I'm not sure we can pull up the last image that Rick showed, which showed the traverse. But I think the question has to do with the area that we call the marginal units, the units on the margin of the crater. The route does traverse across that. It's not on the northern side. It's more on the northwestern side. There we go. So the area where you see the direct east to west traverse, that is across the units that could conceivably have been an ancient shoreline. There are alternative explanations as well. And so the plan is that we will, as Rick said, we will explore the top of the delta, probably take us about the next year, and then we'll do that westbound traverse across the units at the margin of the crater. So we're still intending to get there. It's just going to be about another year.
Thank you. And up next on the phone lines, we have Alex Whitsey with Nature.
Hi, thanks. My question is for David Shuster. I wanted to ask if you could talk a little bit about the types of studies that you could do, especially on these fine-grained sedimentary rocks with organics. When we get them back on Earth, what are some examples of the types of analyses you would want to run on these rocks first thing to see what the organics really mean?
Yeah, this question is one that many of us think about quite a bit. It is very fair to say that these already are the most valuable rock samples that have ever been collected, and any state-of-the-art analytical technique that will be available will be applied to these rocks. In terms of your question about the organics, one of the most important things that we can do is look at a very fine scale, at a much finer scale than we're able to with the rover. So, for example, we could look with various in situ measurements to look at the micron scale, where and what type of organics are seen, what minerals are they associated with. That will inform things like were those organics trapped in certain minerals at certain phases? For example, when that rock became cemented, when the sulfate precipitated. There are isotopic measurements that can be made on a fine scale of this sort. There are basic chemistry observations that can be made on a fine scale. So what we can do in a laboratory is obviously much different than what we can do with the rover. Obviously, the instruments that we have in the rover are extraordinary, and the fact that we can make these observations of organic molecules on Mars to begin with is just awesome. But it's really the level of detail spatially that will be different here on Earth.
Thank you. And then up next on the phone lines, we have Raman Skipa from Wired.
Hi, thanks. This is Ramin. I was a little bit confused, so I'm not sure who I should direct a question to, but I was a little confused about how the sample return will work. Is the plan to have a cache of samples on a flat area that will be retrieved, and Perseverance also deliver samples? Like, are both of those things happening, or are you exploring both and to see what is more feasible, or what exactly?
I don't know if Rick wants to say something first, or I can take this one.
Go ahead, Laurie.
Okay. So right now, as I mentioned, the Perseverance rover, we just did some analyses on its reliability and its expected lifetime. And, Curiosity was mentioned already a couple of times here that Curiosity has already gone more than 10 years and is still going strong. And so we expect that Perseverance will likewise be able to still be operating in very, very good condition when we need to have those samples delivered in 2030. So what the plan is right now, you heard us discussing, you heard Rick talking about potentially dropping as many as like 10 or so samples on the surface in a caching depot over the next several months. That would happen down here in front of the river delta. We know we have a good landing site for the sample return lander in this area. It's very smooth, it's very flat, it's very even. It's a great place for the lander to land. And so kind of as a backup plan, we want to make sure that we're leaving some samples here that we know for sure, if anything happens in the future that would preclude us from being able to get the samples back using Perseverance, we've got this backup cache depot on the surface. And so as we're designing the lander, we're including the helicopters, again, as kind of this part of this backup plan, that if we end up landing in a place where we need to pick up samples from the surface from the cache depot, we'll have those two helicopters. I believe each of them can carry back as many as like 15 tubes. So we'd have more than we need for this particular cache depot. But that's kind of the backup plan. the main plan is that Perseverance will still be going strong. It may, as you heard from Rick, it may be outside the crater. It may extend out and go start exploring outside of Jezero Crater. And, you know, if we can find a good place for the lander to land up there, we'll be looking, of course, and hopefully Perseverance still going strong. Then we can land the sample return lander near Perseverance, and Perseverance can just drive over and drop off the samples there at the lander, not just the duplicates of the ones that'll be at the cache depot, but all of the extra samples, the additional samples that we intend to keep collecting as we continue our exploration. So that's the baseline plan, that we would be able to use Perseverance and that we would drop the lander, you know, deliver the lander somewhere near Perseverance so that we can use Perseverance. But again, if something else were to happen along the way and for some reason we thought Perseverance perhaps was not going to be able to deliver those samples, we might consider a second caching depot at another location. But that's a decision for much further down the line. Right now, as I said, Perseverance is our prime option, and the helicopters at this cache depot we're talking about near the Delta front is our backup option.
Okay, thank you.
Mm-hmm.
Great, thanks. Up next, we have Jim Siegel on the call with NASATech.net.
Hi, everybody, and thank you for taking my question. With respect to the Earth return mission, is the plan to have the SLS launch either from Earth or from the Moon to get to Mars, or would this be some other private company, for example, SpaceX with their Starship? Has that been discussed at all, and where does that stand? Thank you.
Yeah, I'll take that one as well. So we have within NASA, we have a launch service provider contract that we will use, and we'll solicit an appropriate launch vehicle when the time comes for launching the sample return lander. So that hasn't been decided just yet, but we do not need a capability as big as SLS or even as big as Starship. So the spacecraft that we're going to fly there can be launched on existing capabilities. And so we will run that competition like we always do for every interplanetary mission. We compete those, and then we'll select the best launch vehicle and launch provider through that process. And it'll launch from Earth, and it'll launch just as our normal interplanetary missions launch from Earth.
Okay, thank you.
Mm-hmm.
And now on the phone lines, we have Matt Kaplan with Planetary Radio.
Hi, everyone. Congratulations on the collection of these very exciting samples. Part of my question's already been answered, but I'm still curious. As we wait for them to return to Earth, do you ever wish, and I'm certainly not suggesting this would be possible, that Curiosity could drive over to Jezero and add its capabilities? I imagine that has to run through some of your minds.
Yeah, if only rovers could drive that far. Yeah, well, I guess the one thing that I would pick up on is something that Sunanda said, and I'll just say it a little bit differently. You have two very different kinds of capabilities for characterizing both the chemical composition and the organic composition in the rocks. There's the SHERLOC instrument, which makes a map. It is not as sensitive as the SAM instrument on Curiosity. It's a wonderful combination that you could bring together where the SHERLOC instrument could provide spatial resolution and really detailed mapping, and then we could take advantage of the kinds of capabilities that exist on SAM to penetrate deeper and get not only lower detection limits for certain kinds of molecules, but we could actually learn a little bit more about which molecules are present. So that's the thing that I would do if I could bring the two rovers together.
Yeah, I completely agree. That would be what I would want to do as well, so we could get a couple of different views, because that's what I would do on Earth. When we bring these samples back to Earth, if and when that happens, that's what I would do. I would put together the capabilities that Sam has on Curiosity and the things that we could do with SHERLOC, but at much higher spatial resolution, as David was saying, and figure out what's going on in these rocks. So that would be my top dream too.
Rover friends. Now, up next, we have Marcia Smith with Space Policy Online.
Thanks so much for taking my question. I think it's to Rick Welch, but maybe also to Laurie Glaze, and it's about Ingenuity and its relationship to the helicopters that will be on the sample return mission. So, Rick, you said that you hadn't expected Ingenuity to be able to last through the winter. So what is your projection now for how long it's going to last? And what is the difference between Ingenuity and the sample return versions of it? Does it need to be structurally more capable? I mean, if you just put a hook on Ingenuity as it is now, could it lift up 15 sample tubes? I'm just not sure how much of a technological leap it's going to be to take Ingenuity and turn it into something that can lift sample tubes.
Yeah, that's a great question, and Laurie, you can certainly jump in here, but I'll start out, right? One of the great things about having done this technology demonstration is now we have information of how the helicopter really behaves on Mars, right? So we actually know the flight performance, we know the margins, how much it can carry, and that allows us to actually know that we can pick up a full sample tube and actually be able to transport that the 100 of meters between the depot back to the lander, and do it one at a time would be the plan to do that. And so the idea is to leverage the Ingenuity design as much as possible, right, because it's the proven design. And we think we can do that. So we really don't think there's a lot of new technology here. The helicopter does have to have one little sort of new feature. It has to be able to sort of scoot around to get close to the tube. And so we are looking at putting small wheels on the bottom of the legs of the helicopter. It's going to be able to land very close to the tubes, but still need to do that final maneuvering to be able to pick them up.
Yeah, and I think Rick covered most of that. It'll need to have the wheels so that it can maneuver close enough to the samples to allow it to pick up. And it'll have to carry, as you said, a little grapple hook that'll allow it to pick up the grapple that's on the end of each of those sample tubes and carry them back, as he said, one at a time. The helicopter design that we're considering right now really is just only slightly larger than the Ingenuity. And when I say larger, I mean a little more mass, because you do have to carry the wheeled system and the grapple. But the mass is really just a very tiny increment more than Ingenuity. We definitely want to build and take advantage of the technologies that we used on Ingenuity. It was a technology demo and yet has been fantastic. So we don't want to change any of that. We want to use what's worked on Ingenuity.
Thank you. And we have been getting your questions coming in on social. I'll now hand it over to our JPL social lead for your questions.
All right. Anytime we talk about Mars sample return, we always get lots of questions about the safety of bringing samples back to Earth. Laurie, could you talk about how NASA approaches and thinks about planetary protection, especially when considering bringing samples like these back to our planet?
Yeah, and that is a really, really important question, and we want to keep talking about it and talking with the public and getting the public's questions on this. So the first thing I really want to do is stress that right now, the conditions on Mars are really not conducive to life. We really do not expect anything to be alive on the surface there today. Number one, it's extremely dry, it's extremely cold, and life there would be exposed to a really deadly radiation environment with very little atmosphere to protect anything on the surface. That radiation would likely, kill anything that were there on the surface. So it's highly unlikely. The probability of something being alive on the surface that could be dangerous is very small. That being said, we are still being very cautious. We are making sure that when the samples are launched into orbit and then transferred and captured into this capture and containment system on the Earth Return Orbiter, there's multiple layers of seals in there, so that we've done something we call breaking the chain, so that there's no chance of any of the Mars material actually getting outside of that Earth return system and coming into the Earth's atmosphere. All of the Mars material will be contained inside of that Earth return system. We've designed the entry system such that it doesn't even need to rely on a parachute. So one of the biggest risks we have on an atmospheric entry is that the parachute doesn't deploy properly. Well, we've said, let's just bypass the parachute altogether. We will just plan on a hard landing, and we've done many tests of landing a heat shield on hard desert floor, such as they will experience in the Utah desert when the sample return canister comes back, and maintain the integrity of the structure, and particularly the structure of that the sampling container that holds the samples. We'll then make sure that we have all the proper precautions in place as we open and disassemble the entry system. And make sure that we are keeping the sample contained until we're confident that that it's safe to be handled and safe to be distributed for the scientific analysis. And we don't expect that to take terribly long. I just want to say we want to get those samples to the scientists as quickly as possible. Low probability that there's something dangerous, but we're going to make sure that we know.
Thank you. This question is for possibly Sunanda or Dave. Daniel from Facebook asks, is it safe to assume that there will be a program similar to the Apollo moon samples in which a portion of the Mars samples will be archived for decades to take advantage of evolving analysis capabilities?
I'll let you take this one, David. I'll add.
Yeah, actually, I'm actually really happy to have this question because I have worked on Apollo samples, and these samples, I'm gonna reveal my age, but these were collected before I was born. And that archive that happened with the Apollo samples is extraordinary. And of course, the obvious reason for doing this is analytical technologies and laboratories change through time, and they change, in fact, quite rapidly. That said, as you heard today, and I hope you all appreciate, the size of these samples is very, very small relative to the Apollo samples that we collected. But almost certainly, I should have started by saying I don't know the details, but almost certainly some portion of these samples will be archived in a similar manner. Laurie, you may have something more to say about that. I am certain people are thinking this through very carefully, but I will say it's obviously going to be pretty complicated to figure out who gets to measure what on which sample.
It will be, but we have processes in place for doing that, particularly through the Apollo sample programs. We have ways to do that allocation. We're also, of course, working extremely closely with the European Space Agency. We are partners on this Mars sample return mission. And so the one thing that we are planning to do, which is a little different from normal, is that this will be a jointly owned sample, both Europe and the U.S. These are our samples. It will be a collection that is for everyone, and we will probably curate it in different places, but we'll have the process for allocating those. And absolutely, there are plans to preserve significant fractions of the samples for future. That's, as you said, that is the incredible value of these sample return programs that we have, is that we can save large fractions of the sample, as you say, for future analytical capabilities, for new hypotheses to be tested in the future that we don't even know to test yet. And we've seen that demonstrated with the lunar samples, with the most recent samples that were opened, almost 50 years after they were collected, still in their pristine sealed sample tubes. Fantastic opportunity to test new hypotheses and allow the new generations of scientists to look at those samples.
Sunanda, did you have anything you'd like to add?
No, I just want to agree with that. I just wanted to bring up one point from studies on Martian meteorites. Some of those, for instance, those give us an idea of what Mars is made up of, and those have been studied for decades. Like, I studied one last week, and that's been studied for a really long time, and we have newer capabilities in the lab, as Dave was mentioning, that we didn't have when they were first discovered. So it's a really great opportunity for science to develop, and I think getting new samples will really spur the development of new technology. So I'm excited to see that happen.
Thank you. And we have lots of questions still coming in. Let's go back to the phone lines. We have Marina Koren with The Atlantic.
Hi, Marina with The Atlantic again. I am looking at the names of each sample, and I'm wondering what naming conventions you're using, specifically Hazeltop and Bearwallow, which I believe you said are the samples that you're most excited about. And perhaps if they contain what you're hoping they contain, these names might become more famous in coming years. So I'm curious how you've come up with all of these. Thanks.
Yeah, I'll answer that. We have a grid that is laid down on the map of the crater floor, and each box of this grid we have associated with a national park or preserve somewhere in the world. And so we take the names off of a map of that national park or preserve and assign it to the targets. And so we do that with lots of different targets. So you heard us use lots of different names, not just Berry Hollow and Skyland. We have all of these names are pulled off of the map, and the map that we are pulling names off of that you've just been hearing about is Shenandoah National Park in the eastern United States.
Thanks, Ken. And we now have a follow-up question coming in from Ken Chang with the New York Times.
Thanks for taking my question, Ken. Obviously, you won't know for years until the samples come back to Earth. But at this point, if you were betting, would you bet that there's actual biosignatures in these rocks?
Let's just say we are not going to bet.
Yeah.
We're going to decline.
We're going to look at the data.
All right, and let's take it back to the phone lines. Next up, we have Ken Kramer with Space Up Close.
Hi, thank you for taking my question, and good luck congratulations on everything you've done so far. I'm wondering about why do you think that these samples are aromatics, the organics? Why do you think they're aromatics? And do you see any evidence for any functional groups like amines, halogens, hydroxyls, anything like that? Thank you.
Yeah, that's a really good question. So I'll first start by giving a little more information about SHERLOC. So SHERLOC doesn't see all organics equally. It has sort of a preference, and aromatics is something that we would sort of preferentially see because there's some enhancement that we have. So that's why we think when it's showing up, and it's showing up so clearly, more likely that it looks like aromatics. And then we also have analog instruments here at JPL and a couple of other places that we have reference libraries that we've built up. So basically every time we get signals, we compare to our reference libraries that we've developed using the analog SHERLOC instruments and then compare to see what those signals look like. So that's why we think that this one is aromatic because it matches the things that we're seeing in the library. And then what was the last part of the question? I think I missed something.
Any functional groups like amines, halogens, hydroxyls, what are on these aromatics, if you might know?
I don't think the data can tell us that yet. I think we gotta get those back and find more information about it because the data that from the surface will only tell us so much.
All right, thank you.
Well, that is all the time we have for questions today. Thank you so much to our speakers, and thank you for your questions. If you have additional questions, please contact the media line at 818-354-5011 if you have any follow-ups. And for more information on the mission, visit nasa.gov/perseverance and mars.nasa.gov/perseverance. And we've got a new feature on the Perseverance site where you can do a deeper dive on the samples we've collected. So check out mars.nasa.gov/mars-rocks-samples. And don't forget to follow us on social media at NASA Persevere. Thank you for watching.